Welcome to the pre-class video assignment for section 3.4. Here we're going to talk about inverting Laplace transforms, finding the inverse. There is apparently an analytic method for doing this, but we're going to totally cheat and just use basically the Laplace transform tables in reverse. That might sound easy, but it can be a little tricky to make something match up. So that's kind of what we're going to discuss a little bit. So we're going to look at some simpler examples and some prerequisites for the remainder of the section. The inverse Laplace transform, this is not a very earth-shattering definition. The inverse Laplace transform is basically, if you know what f of s is, you want to be able to figure out which is the little f of t that it came from. We basically are trying to reverse this process of finding a Laplace transform. So notation for it, for inverse Laplace transform, is just L inverse. So this is reminiscent of algebra. F inverse is the inverse function of f. So that's the nature in which we're using this here. This is not a reciprocal. This is just meant to mean an inverse. So this says undo the Laplace transform big F of s to find the little f of t that it came from. So again, I read that there is a method for doing this. I've never seen it. So in practice, what we do is we simply look them up in basically we're using the Laplace transform tables in reverse. A couple of easier examples then here. So what is the inverse Laplace transform of s over s squared plus 49? So again, to do something like this, I would go to my Laplace transform table, and we're looking for s over s squared plus 49. So I'm just scouring my table to figure out one that looks like this. So here we have one that looks like that. This is s over s squared plus k squared. So my k squared is 49, so my k is 7. So apparently cosine 7t is my inverse Laplace transform here. So that's what we got here. It's really just look it up. This one's pretty direct off the table. And then again, I basically used number 8 off of that table in reverse. Here's another one, fairly straightforward. If we look at 2, what is the inverse Laplace transform of 2 over s minus 1 all cubed? What would this be? And again, we need to match this up with something on our table. So let me just jump back and forth a little bit. 2 over s minus 1 cubed. We want to look for a Laplace transform that looks like this. 2 over s minus 1 cubed. This is going to be like this guy here. S minus 1 cubed. So if 2 is supposed to be the number on top. So this is our Laplace transform, n factorial s minus a n plus 1 factorial. So if we look at that guy here, then how do we undo this? So basically here, my a value, so this was n factorial over s minus a to the n plus 1 is the rule. This is t to the n and then e to the at, according to number 17 on the table. So in order for us to match that up here, I need to have, okay, I have s minus 1 to the 3, which is s minus 1 to the 2 plus 1. So n is 2. Therefore, I need a 2 factorial in the numerator. 2 factorial is 2, so this just happens to work out. So here we have n equals 2 and a equals 1. So this would be our n equals 2, a equals 1. This would be what works. And this is from number 17 in the table. So those two are fairly easy because they're fairly directly from the table. So start off here with a couple of on my open math that are fairly straightforward like this. Try to look them up on the Laplace table, Laplace transform table. And then there's a second one. All right, so of course, not everything is quite as simple as that. They do not always exactly what shows up on the table. So we do have to do some manipulations and what have you to try and match up a function we're trying to invert with something that is on the table. One of the easier things we can recognize is linearity. That is, The inverting a Laplace transform is also linear, and this should not be a surprise. We learned that Laplace transforms is a linear operation, so inverting it will also be linear. So this just means basically the following. That is, you can invert Laplace transforms term by term, term-wise, and move constants out in front. So this should make perfect sense because doing the forward Laplace transform is also linear. So for example, how do we find an inverse Laplace transform for something like this? This is the inverse Laplace transform of 3 over s minus 2 over s cubed plus s plus 1 over s plus 2. So again, linearity tells me I can really just think of these one by one. I can do the Laplace inverse of 3 over s, that is just the Laplace transform of a constant, so undoing it is just 3. This is the Laplace inverse of, again, this is s2 plus 1. That means it should have a 2 factorial on top, which is 2. It already does, but there is a minus sign there. So, oops, that should be a minus. My bad. That should be a minus. And then this one here, this is number 11 on the Laplace transform table. Read this as 1 over s minus negative 2. So a is negative 2, and we have e to the minus 2t. So again, we can just read them off term by term. So try one of those. Okay, so someone slightly more complicated. What is the Laplace inverse of 10 over s plus 2 to the 4? All right, so again, my first goal here is I'm going to go and look for something similar to this in my table. So if we go to our Laplace transform table, with a bit of searching, you would hopefully come up with that this looks a bit like a number 17 here. This is a number 17, right? So we have this situation here. So we have here a number 17. So if I read this appropriately, matching it up to number 17, I want this to be s minus negative 2. That's how we get s plus 2 here. So a is negative 2. So I have an a equals negative 2. In the numerator, well, let's see, in our power here, we have a power of 4. We'd read that as being a 3 plus 1, therefore n equals 3. So here in this one, we have an n equals 3, and therefore 3 factorial is what should be sitting in the numerator, which is a 6. So we don't have a 6 sitting in the numerator, so I have to fix that somehow. I have to make a 6 there, but I still need this to be equality, yes? So the idea here, and this is a little manipulation trick that we need to be familiar with, and that is, this is how I would write it, basically. I can pull the 10 out in front. I can put the 3 factorial there that I needed. 3 factorial is 6. So I also divide by 6 in order to cancel that out. So effectively, I am multiplying this by 6 over 6. Multiplying by 6 over 6. I'm leaving the 6 in the numerator inside and pulling the 10 over 6 outside. So that is a little trick that we need to be able to see to manipulate these things sometimes. So I have a little exercise in my open math for doing something like that little sort of manipulation trick. So give that a go. So once we see that manipulation trick, then we're right there, yes? This now matches up with number 17 in my table. That is, a is negative 2, n is 3. So this right here should invert to t cubed e to the minus 2t. T cubed e to the minus 2t, and then to fix it, we also had this 10 over 6 on the outside, which can be reduced to 5 over 3. So this would be our inverse Laplace transform. All right, so give one of those inverse Laplace try one a little bit like that. All right, here is another example, a little bit more complicated. What is inverse Laplace transform of minus 2s plus 6 over s squared plus 4? So how do we invert something like this? Again, we need to go to our table. in Laplace transform tables, we will notice that. And again, this is kind of important. You want to kind of start getting familiar with this table and remembering some of these things. So with a bit of practice, it doesn't feel like quite so much searching. But basically, our denominator in this example looks a lot like these. It's like a 7 and 8. We've got an s squared plus k squared in the denominator. One of them, the sine one, has just a number in the numerator, but which is matching up. So this is k squared, this is k. The other one has a s in the denominator, excuse me, s in the numerator and a k squared in the denominator. So that's not exactly what we have, but again, we can make this work. So my idea here is to break this up. I've basically got a minus 2s over s squared plus 4, and I've also got a 6 over s squared plus 4. So we have minus 2s over s squared plus 4 plus 6 over s squared plus 4. And of course, the 4 can be read as 2 squared, hence the k number here is 2, yes? So in the numerator, again, I want this minus 2 to be factored out here because I wanted this to be just s. This is now looking, I believe that's number 8 in the table. That right there is number 8. So we've got a minus 2 times number 8 where k equals 2. The other one here is a 6 over s squared plus 2 squared. And of course, this matches up with number 7 if this was a 2 and not a 6. I want that to be a 2 and not a 6. Again, this one's actually pretty easy. That means I can just factor out 3 out in front, and then I would have a 2 left behind. And then this is a number 7 off my table. So I have a minus 2 times, and then this is number 8 off the table is cosine kt, where k is 2. And this one is number 7 off the table, which would be a 3 sine 2t as well. So we can see that. So again, we need to sort of practice these kind of manipulations. So here's a little example of that to practice on. And then there is an actual invert a Laplace an inverse Laplace transform to try on my open math. Try that one. And that's kind of where we're going to leave it with the notes. We will pick the notes up from here going forward. I do want to sort of look at some of the prerequisites, some of the things we're going to need to see going forward. So we've looked at some of these actually easier situations here. What happens when we have something a little bit more general, a little bit more arbitrary? So when this is a polynomial in the denominator, we really have 2 cases to worry about. One case is when this polynomial factors. Guess what? If it factors, we can apply PFD to it to break it down and make it something more palatable. If it does not factor, like this one does not factor, then the trick here is to complete the square on it, So we will do this example in class, but I want you to remind yourself how to do some completing of the square. So here's a little write-up of it. I'm not going to talk through it. Here's a little write-up for completing the square. If you want a little reminder, pause this video and take a little read or look it up for yourselves. That you can do this a little bit later. But there are a couple of completing the square problems to try just to review how that works. So here's the first one. And then there's a second one. All right, so completing the square is one trick that we need to manipulate some of these things. And again, completing the square comes into play when we have a quadratic in the denominator that does not factor. Then we complete the square. In any other polynomial in the denominator, what we will be after, so examples such as this one, and maybe some others further down, is that if the denominator does factor, then we are doing partial fraction decomposition. So again, we should be able to remind ourselves how to do partial fraction. We've reviewed this a couple of times here and there, but in general, they can be a little bit more involved in this section, some of these higher cases for partial fraction. So give those a bit of a practice. Now, before I send you off to do that, I did write up a summary of partial fraction decomposition, mainly the 4 cases of what the 4 cases look like and what they look like to set up the PFD in each of them. We've probably practiced this one a couple of times. Here is a couple of examples that might involve probably cases 2 and 3. Probably, I don't believe we will. Generally, case 4 is a bit messy and is avoided in exercises, but you should practice some of these. So here's the first one. And then there would be a second one to practice. All right, so one last thing to look at is once we have, so for example, again, we will work through this example together in class, but we do have this sort of situation that if we work on our denominator by completing the square or partial fraction decomposition, we end up with something that looks like this. If you look at this after we complete the square, this, if you look at our tables, if you look at this, these end up looking like a number 18, number 19 case in the denominator. So that is kind of what you're shooting for when you have a completing the square situation. But again, this generally often will require some manipulation of this expression. Once you've completed the square, we would still need to manipulate it into a form where we can recognize cases for number 18 and number 19 from the table. Again, we will work this problem together in class, but I do have a little exercise to practice this sort of manipulation on my open math. So take a look at this one and just give it a go. All right, and that is it. So we will pick up from here in our notes together in class and work through the rest of this together. And otherwise, that will be it for now. Thank you.